Welcome back to our journey through the cosmos. If you enjoy clear, step-by-step explanations of big scientific ideas, don't forget to subscribe, like, and share this video. Your support helps our channel grow and keeps us creating quality educational content. Thank you very much. Now, let's return to our journey through the cosmos. Last time we explored the incredible scale of the universe, from planets and stars to galaxies and clusters, and discovered our cosmic address. But there's a big question we have not answered yet. Is the universe sitting still? The surprising truth is it is not. Everything, everywhere is moving away from everything else. Our universe is expanding. To understand how we discover this, let's start with something familiar: sound. Have you ever noticed how the pitch of an ambulance changes? Consider an ambulance siren at rest, which emits a sound of a specific frequency in all directions. Sound waves travel at the speed of sound in air, which is independent of the speed of the source or the observer. Four successive wave crests are shown. The distance between two successive crests is the wavelength. You should know that wave speed is equal to the product of wavelength and frequency. This is the fundamental wave equation. Since the source and observer are at rest, the wavelength and frequency remain constant. However, when the sound source is in motion, things change. If our source, the ambulance, is moving, the siren emits sound at the same frequency as when it is at rest. But the sound wavefronts it emits forward, in front of it, are closer together than when the ambulance is at rest. This is because the ambulance, as it moves, is partially catching up with previously emitted wavefronts, emitting each crest closer to the previous one. Thus, an observer on the sidewalk in front of the ambulance will detect more wavefronts per second. Therefore, the wavelength is shorter and consequently the frequency is higher because the speed of sound remains the same. The frequency heard by an observer on the sidewalk will be higher. The wavefronts emitted behind the ambulance, on the other hand, are further apart from each other than when the ambulance is at rest because the ambulance is moving away from them at high speed. Each new wavefront emitted is further away from the previous one than when the ambulance is at rest. Therefore, fewer wave crests per second pass an observer behind the moving ambulance, and the wavelength is longer, and consequently, the frequency is lower. In short, when a sound source moves toward an observer, the tone the observer hears is higher pitched than when the source is at rest, and when the source moves away from the observer, the tone is lower pitched. This phenomenon is known as the Doppler effect and occurs for all types of waves, including light. The Doppler effect is a change in frequency or wavelength of a wave in relation to an observer who is moving relative to the source of the wave. Before we go further, let's take a quick look at the electromagnetic spectrum, specifically the tiny part we can actually see, visible light. The visible spectrum includes all the color of the rainbow: violet, blue, green, yellow, orange, and red. Each color corresponds to a different wavelength of light. Violet and blue light have short wavelengths, around 400 nanometers. Red light, on the other hand, has longer wavelengths, about 700 nanometers. The Doppler effect also applies to light. When an object is receding, that is, moving away from an observer, the peaks of the radiation that are emitted will be spaced farther apart than they would be if the source object were stationary. The result is that the resulting wavelength of light appears longer. Astronomers say that it is shifted to the red end of the spectrum. Conversely, when a source of radiation is approaching an observer, the wavelengths of light appear closer together, effectively shortening the wavelength of light. Astronomers say that it is shifted to the blue end of the spectrum. So when we talk about light being redshifted, it literally means those light waves are being stretched, shifted toward the longer, redder end of the spectrum. Well, you might be wondering, okay, I understand the Doppler effect and the redshift, but how do astronomers know and measure the wavelength of light these galaxies emit? It all starts with atoms, specifically hydrogen, which is the most common element in the universe. Electrons can only exist in spatial energy levels around an atom. Electrons can change levels, but to jump to a higher level, they must absorb energy to match the higher level. An electron can only absorb or emit energy that allows it to change levels, so it can only interact with certain colors of light. For example, imagine light passing through a tube of cold hydrogen gas and being split by a prism. The spectrum will exhibit well-known and studied absorption lines. The light emitted by galaxies comes from the hot gas within them. Galaxies are surrounded by cooler gas composed primarily of hydrogen and helium. As this emitted light travels, it passes through the cooler gas surrounding the galaxy, which absorbs specific wavelengths, leaving behind dark lines in the spectrum. When astronomers compare these patterns with those we measure on Earth, they find the same spectrum, just slightly shifted toward the red. Now that you know how astronomers can measure the wavelength of light emitted by a galaxy, let's turn our attention to the Doppler effect, but this time applying it to light. The Doppler effect for light is given by the formula. Lambda 0 is the rest wavelength measured in the laboratory. Lambda observed is the observed wavelength of the galaxy. Beta is the ratio of the galaxy's receding velocity v to the speed of light. V is the galaxy's receding velocity. V is greater than 0 means away from you, and V is less than 0 means toward you. You are probably curious about how to apply the Doppler effect of light to calculate the speed of some known galaxy. So here's an example. The diagram shows two lines due to calcium absorption in the spectra of two galaxies. From nearby Virgo to the very distant Hydra, Each diagram gives the wavelength of the H-alpha spectral line. The H-alpha line from hydrogen has a wavelength of 656.3 nanometers in the laboratory. Estimate their receding speed. This redshift tells us that the galaxies are moving away from us, and we can calculate their speeds using the formula for redshift. Solving for beta, we get the receding speed of Virgo, which is only 0.4% of the speed of light. For Hydra, we get a much higher receding speed, around 18.3% of the speed of light. The magnitude of the redshift is specified by the Z parameter and represents how much the wavelength has increased. That is, where delta lambda is the change in wavelength, lambda 0 is the wavelength measured in the laboratory. By comparing the observed wavelength with the laboratory value, we can calculate the redshift of each galaxy. For Virgo, the wavelength increased by 0.4%. Note that 0.4% represents the same ratio between Virgo's receding velocity v and the speed of light. For Hydra, the wavelength increased by 20.1%. Note that 20.1% does not represent the same ratio between Hydra's receding velocity v and the speed of light. For Hydra, this ratio is 18.3%. The difference you see between the change in wavelength and the ratio beta is due to Einstein's special theory of relativity. Let's rewrite the formula for the Doppler effect of light, but now as a function of the parameter z, that is, the redshift. Now we will see how this formula changes when the velocity v is much less than the speed of light c. First, square both sides. We can rewrite the right-hand side of the relativistic formula as a geometric series expansion in beta. Replace x with minus beta and n with minus 1. The binomial expansion approximation is used when the absolute value of x is much less than 1, so that the quadratic terms are negligible. Since the speed v is much less than the speed of light c, we have beta much less than 1. We can apply the binomial expansion approximation. Substitute this back into the relativistic formula and take the square root of both sides. Subtract 1 from both sides. If the speeds are non-relativistic, v much less than c, then beta is small and z will also be small. Then the Doppler formula is: in other words, when the redshift z is small, the redshift is directly proportional to the speed v. Now that we know a little about the Doppler effect of light and what redshift means, let's look at how Hubble discovered the expanding universe. In the 1920s, Edwin Hubble used the inverse square law in conjunction with the period luminosity relation for specified variable stars to calculate accurate distance to many galaxies. The formula is: this law states that the apparent brightness of a light source decreases with the square of its distance. At the same time, other astronomers, mostly notable Vesto Slipher, measured the redshifts and respective recession velocities of several galaxies. This means they were moving away from us. In 1929, Hubble then combined his distance data with velocity data collected primarily by astronomer Vesto Slipher. Hubble plotted the recessional velocity v against the calculated distance d for many galaxies. He found a straight line relationship. This proportionality means that the farther a galaxy is, the faster it is moving away from us. The constant of proportionality is the slope of the graph and is known as the Hubble constant. This became known as Hubble's law. V, speed galaxy, is moving away from redshift. D, distance to the galaxy. H0, Hubble constant, rate of expansion of the universe. The current value of Hubble constant is about 67 km per second per megaparsec of distance, with an uncertainty of about 1.2 km per second per megaparsec. We can combine the redshift z for non-relativistic velocities and Hubble's law to obtain a formula for calculating distance from redshift. By setting the two expressions for speed v equal to each other, we create a powerful formula to estimate distance directly from the measured redshift. This formula relates distance to redshift. The Hubble's law meant that space itself is expanding, not just galaxies moving through space, but space stretching between them. Imagine a balloon with dots drawn on it. Each dot represents a galaxy. As it expands, what happens to the distance between the dots? They move farther apart, not because the dots are moving across the surface, but because the surface itself is stretching. Even if you were on any one dot, you would see all other dots moving away, just like we observe galaxies moving away from Earth. We are not at the center of the universe. Every point in space sees expansion happening in all directions. Galaxies are not flying away through space like rockets. It's space itself that is expanding. If you mentally reverse the process, it means everything was once packed into a much smaller space. This observational evidence was the first strong proof that the universe is not static, overturning the prevailing scientific view and laying the foundation for the Big Bang theory. Hubble didn't discover the expansion of the universe in a single step. He provided the empirical evidence that proved it. Let's summarize these steps. Here's how he put the pieces together. 1. Establishing the cosmic distance, applying Henrietta Swan-Leavitt's period luminosity relation. Hubble calculated the distances between Earth and many nearby galaxies. Hubble also proved that the spiral nebulae were not clouds within our own galaxy, but rather independent galaxies far beyond the Milky Way. 2. Measuring the cosmic velocity. Slipher discovered that the spectral lines in almost all galactic spectra were shifted toward the red end of the spectrum, meaning that the galaxies were receding from Earth. The greater the shift, the greater the velocity. 3. Hubble's law. The conclusion. Hubble plotted the recessional velocity v against the calculated distance d for many galaxies. He found a straight line relationship. The only physical model that makes sense of this uniform recession from every observer's point of view is that space itself is expanding, taking the galaxies along with it. If everything is moving away from everything else, space itself must be expanding. And if we imagine running this cosmic expansion backward in time, all galaxies, all matter, all energy come together in an incredible hot and dense beginning. That moment is what we call the Big Bang. And the evidence is all around us. Every redshifted galaxy is a clue to our expanding universe. But can we find even stronger proof of this cosmic beginning? In our next lesson, we will look at the faint afterglow of creation, the cosmic microwave background.